In dynamical systems, there is an accepted practice for finding coherent structures, ocean gyres, atmospheric vortices, and mixing boundaries. You construct an Ulam transfer operator from the data, compute its eigenmodes, and assume the subdominant eigenvectors will reliably map out the underlying geometry. To test that assumption, we are going to audit a specific mathematically hostile environment. This is the twisted bird map, evaluated at an epsilon of 0.70, yielding exact 16,384 by 16,384 column stochastic Ulam transform matrices. This specific map is highly non-normal. Its left and right eigenvectors diverge sharply, creating a skewed matrix architecture that makes it a perfect stress test for the standard Ulam methodology. Continuous theory assumes infinite precision, but in reality, we process these matrices on finite grids, strictly constrained by the 64-bit limits of standard computing hardware. We cannot assume the continuous mathematics survives the discretization process intact. If we want to trust the resulting physical maps, we have to rigorously audit the finite grid computation itself. We use a two-axis diagnostic protocol to determine if hardware noise is overpowering the mathematical signal. Axis 1 measures precision collapse. First, we compute eigenvectors in float 64. We calculate the condition proxy, kappa j, representing divergence between left and right eigenvectors. Then we introduce the hardware drift bound, epsilon Mach. Multiplying the condition proxy by this drift bound establishes the Bauer-Fike worst-case eigenvalue perturbation. Here is the failure threshold. If this worst-case perturbation equals or exceeds the absolute value of the computed eigenvalue itself, that specific eigenmode tier is flagged as a precision kill. When a tier fails this axis, the computed eigenvalue has been entirely swallowed by machine rounding error. Mathematically, it is indistinguishable from random hardware noise. The second axis measures observable disintegration. This tracks the physical collapse of the eigenvector's spatial support on the grid. We calculate a support ratio, sigma j. This is the ratio between the minimum number of cells required to accumulate 90% of the mass for the left eigenvector, divided by the same metric for the right eigenvector. If that support ratio equals or exceeds 100, the spatial lana has sheared apart. We flag that tier for observable disintegration. This diagram illustrates the protocol. Tiers enter the killing zone when both axes fail. On the bird map, 18 of 20 subdominant tiers fail completely. Even Tier 1 exhibits catastrophic collapse. Its left eigenvector spreads across 14,746 cells, while the right collapses to 1. On this exact grid discretization, the Ulam method suffers a 90% failure rate, destroying any physically meaningful coherent structures in the deep spectrum. Is this failure rate a universal flaw of all non-symmetric Ulam operators, or is it an artifact specific to the bird map? To find out, we run a negative control. This is the Agulhas operator, built entirely from publicly available surface drifter trajectories in the Southern Ocean. We pass this real-world data through the exact same raw asymmetric box counting pipeline, testing it across grid sizes of 2,048, 8,192, and 18,432 cells. Out of the 30 tiers scanned across those three grids, exactly 0 fall into the killing zone. While we do observe some high condition numbers near the spectral boundary, the observable support ratio never exceeds 10 on any single row. When applied to highly complex advective ocean dynamics, the Ulam method remains stable and structurally observable. For our second negative control, we test a canonical smooth-flow mathematical model, the widely used rotating double-gyre. This operator is generated natively in Python and tested across 4 increasing grid sizes, scaling all the way up to 32,768 cells. The results replicate our ocean data. Out of 40 scanned tiers, 0 fail the simultaneous two-axis test. Across all grid sizes and all tiers, the maximum observed support ratio peaks at just 41.5, keeping it safely below the disintegration threshold. Both the observational ocean data and the canonical theoretical flows confirm that under normal structural conditions, the Ulam methodology operates reliably. This readout compares our 3 subjects side by side. For tiers 3 through 10, only the bird map triggers the severe observable ratio, alongside precision collapse. Extreme condition numbers alone don't cause failure. It requires the catastrophic spatial collapse seen exclusively in the bird map. The killing zone is a geometric artifact specific to the discretization of the twisted bird map. Non-normality alone does not universally break the Ulam method. When confronted with unstable non-symmetric operators, the standard literature often employs a specific mathematical intervention. Researchers will force the operator into normality via symmetrization, typically using this equation. By applying this adjustment, the asymmetric matrix is rendered self-adjoint. A self-adjoint operator trivially forces the condition proxy for all tiers to equal exactly 1. The divergence between left and right eigenvectors vanishes. On paper, this shortcut appears to instantly cure the operator, completely bypassing the precision collapse axis. That mathematical stability comes with a severe physical cost. The resulting eigenvectors no longer represent the raw advective eigenmodes of the original system. Instead, they represent a pi-weighted reversible process. Because symmetrization overrides the precision check, the underlying physical collapse of the grid geometry is never interrogated. The massive condition proxies of the bird map are artificially flattened down to 1. Symmetrization acts purely as a mask. It hides the condition number explosion without recovering the actual coherent structures on the finite grid. By forcing mathematical symmetry onto an inherently asymmetric grid, we blind ourselves to the actual numerical killing zone lurking within the discretization. To be perfectly clear on the scope of this analysis, all of these conclusions are strictly bounded to the exact n-by-n finite grids executed here. None of this invalidates the continuum Navier-Stokes equations, nor does it challenge the mathematics as the grid approaches infinite resolution. But on a finite grid, subdominant eigenvectors do not universally delineate coherent structures. If the underlying discretization is pathological, the resulting geometry is noise. The Ulam method is reliable when applied to structurally sound data, like the Agulhas drifters or the double-gyre. But the twisted bird map proves that blind trust in finite grid outputs, or using symmetrization to hide instability, is analytically fatal. The continuous mathematical theory remains pristine, but without a rigorous two-axis numerical audit, the computational lens will inevitably lie to us.